So, by the way, how many of you can solve this question? Okay, very good. Very good. So, that means you are able to relate what you have learned previously to what you are learning now. I think that's important. Closing the gap among the different area of knowledge you have acquired. Okay, so I'll give you a brief picture first. Now, let's say that we have this copper, right, isolated, and now we shine light and assume that the photon energy is greater than the work function, so you can free electron. So what happens? Let's say when the first photon drops, right? So you get one electrons out, and for every electron that is free, liberated, there will be a positive charge induced, isn't it? And that comes from the metal ions. So now let's say we have already 4 electrons free, now you got 4 positive charge and so on. Okay, so as you can see from here, as you get electrons liberated from the metal, the sphere becomes more and more positively charged. Agree? Right? And when it becomes very positively charged, in fact, it will exert an attractive force on the electron that's trying to leave. And this attractive force will increase when more and more electrons are being free. Because when more electrons are being free, you'll be charged more positively, so the attractive force becomes stronger and stronger. Now, you expect that at some point, when so many electrons have been free already, such that this sphere is very positively charged, any electrons trying to leave may be pulled back. And that indeed happened. So up to a certain point, no matter how hard you shine light, you don't get any electrons coming out anymore. Because whatever that comes out, get pulled back. That's the gist of this question. Is it clear? Okay, now how do you solve it? Now we understand it from the force perspective. How do you solve it? You can solve it using the energy perspective. Huh? Now, remember that if I have a spherical conductor having a certain charge Q, how does the potential of the conductor looks like? Outside, inside. Remember, it will look something like this. Inside the conductor, the potential will be constant, given by KEQ over R. R is the radius, Q is the total charge on the sphere. Okay? And this is what is inside. Outside the sphere, the potential will drop as 1 over R. Do you remember this? Okay? So here I just want to highlight something about the direction of electric field. The electric field will be directed to the right, increasing R, because it's directed from high to low potential. So when electrons are trying to leave, what happens? They will be experiencing an electric force which is in opposite direction to E. Therefore, this electric force is trying to pull them back. Can you see that? Okay? Now, also realize that the potential of the sphere builds up with the charge. So when more electrons are being free, Q will increase. So this potential will increase. So when the potential gets larger and larger, what happens to the slope? The slope gets larger and larger. So the electric field gets larger. Then the electron will experience a strong pullback force. Okay? Now, so this is a force picture. Let's look at the energy picture. So what we have obtained here is the potential of a sphere when it contains a charge Q. Now, how about the potential energy of electron? If you are given the potential in a space, are you able to find the potential energy of electron or any charge? Yes, because potential energy is just the charge times the potential, isn't it? So I take VR multiplied by minus E. Then the function I obtain will be the potential energy of electrons. So when you take this purple curve multiplied by minus E, you'll get this green curve. It's now negative. So this gives us the potential energy of electron inside the sphere and outside the sphere. Is it clear? When the electron is free, it's at infinity. And infinity, we take the reference as zero potential, so it's also zero energy. And now the electrons inside is at a negative energy. What does it mean? It means that if you want to free the electron, you must give electron this amount of energy. And this amount of energy is given by this red arrow here. This amount. You see that? So this is something like a barrier. The electron, if it can come out, it must overcome this barrier to become free. Correct? Okay. Now, what is this barrier? So we come back. Vs, this potential, right, is Keq/R. So the Vus, the potential energy of electron in the sphere will be Vs multiplied by minus E. So this is what I'll get. Okay. And then the barrier height that the electron is facing is U at infinity subtract U at S. And if you take the difference, you get EKEQ/R. So therefore, this is the barrier height. Is it clear? Now, can you see that the barrier height actually gets larger when the sphere is more and more charged up? Okay? So from here you can understand, initially, when the Q is very small, when you just start your experiment, not a lot of charge free yet, Q is very small, so the barrier height is very small. So when you do the photoelectric effect experiment, the kinetic energy of the electron will be large enough to overcome this barrier, so it can become free. But as the experiment continues, Q will build up with time. And when Q builds up with time, right, this barrier will get larger and larger. So subsequently, electrons find it harder to leave. Now there will be a point whereby this barrier height just exactly equal to the maximum kinetic energy. What happened? At that point, it means that is the limiting point. From that point onward, no electron can come out. Because whatever comes out, it will just fall back again. They don't have enough energy to surpass the barrier. This is just like, if you remember your mechanical engineering picture, there's a hill there, a person is trying to run across the hill. Can you run across the hill? It depends on your initial kinetic energy and depends on the potential energy of the hill. If your kinetic energy can surmount that potential energy of hill, then you can cross the hill. Otherwise, you fall back. It's exactly the same here. Is it okay? So therefore, this is the equation that we shall use to solve the problem. The limiting condition whereby no more electrons can be free happens when the maximum kinetic energy just equal to the barrier height. So at this point, anything that comes out will fall back because of this attractive force. Okay? So setting that equation, so first of all, we find what's the Kmax from the photoelectric effect equation. And we use this equation, we can calculate what is the charge. Now what it means is that when the sphere is charged up to 8.3 times 10 to the power minus 12 Coulomb, then no more electron can be free. You can convert what is the number of electrons equivalent here is equivalent to 5.2 times 10 to the power 7 electrons. So what it means is that once that number of electrons have been freed, subsequently no more electron can come out. Therefore, this is the amount of charge that will be built up in the sphere. Is it clear? Okay, just one short question. Time is running out. How come this is not being discussed when you learn photoelectric effect? When you learn photoelectric effect, you learn all the standard equation, right? Like what we have seen in question 4. But we don't discuss about this effect. Can anybody explain why? This one is simply telling us that if you have a conductor, if I shine light, in fact there's a limit to how much charge you can generate, how much electron you can free, right? But why this is not discussed when you learn your photoelectric effect? What's the difference between this problem and the general photoelectric effect setup? The answer lies in the photoelectric effect, you have a closed loop. So whatever electron that comes out, right, is collected, is fed back to the same piece of metal. So you don't let charge build up. You know what I'm trying to say? Alright? You actually have a circuit so that charge collected enter into a circuit and comes back to the metal. And then you get more electrons free, but this electron, whatever free, they will come back. So the conductor that you are doing the experiment is never allowed to charge. It's always considered as a neutral state because the electrons come out, feedback, come out, feedback. But in this problem, it's an isolated sphere. So that once it's charged up, there's no feeding back of charge, isn't it? So you build up a positive charge. So there's a difference, okay? You have any question?